In this session, after recalling the main concepts of monotonicity, we shall switch over to deal with the next topic. First of all, let us recall the main concepts of monotonicity. We see and we recognize that a particular function is monotonic when and only when it is either monotonically increasing, monotonically decreasing, monotonically non-increasing, non-decreasing, like that. That is, if x1 less than x2 for all points x1 and x2 belong into the domain of the function f, if this happens, we recall that f is strictly increasing. For all points x1 and x2 belonging to the domain of the function, if this happens, that is x1 less than x2 implies f of x1 less than or equal to f of x2, then f is monotonically non-decreasing and this is strictly increasing. Similarly, if x1 less than x2 implies f of x1 greater than f of x2, then f is strictly decreasing. And if a condition of this sort happens, then is satisfied, then we say that f is strictly non-increasing. Out of all these four cases, we say that f is monotonic. Okay, how can we recognize that a particular function is monotonic? What is the test to examine whether a given function is either increasing or decreasing? That is, it is monotonic. The derivatives, the differential calculus will help us a lot in deciding this factor. That is, if a function say f of x is given, how to decide the monotonicity. We shall be looking at that concept. If for a particular function say f of x, if f dash x greater than 0 for all x belongs to closed interval a to b, where closed interval a to b is a subset of the domain of the function f, then we say that f is increasing on the closed interval a to b. Accordingly, if f dash x greater than or equal to 0 for all x belongs to that, then we say that it is non-decreasing. Similarly, if f dash x less than 0 for all x belongs to closed interval a to b is observed, then we notice that f is strictly decreasing in that particular interval. So for increasing character f dash x must be greater than 0 and for decreasing character f dash x must be less than 0. Accordingly, f dash x less than or equal to 0, f dash x greater than or equal to 0 will give us the conclusions strictly non-increasing and non-decreasing, like that. Well, let us observe a simple, very simple example for this nature of functions. Please notice this problem. The given function is f of x is equal to x bar x. We are supposed to test the domain in which the function is monotonic, that is increasing. It's very simple. For increasing character, what should you observe? F dash x must be greater than 0, isn't it? But you see, f of x is equal to x bar x is given. What is f dash x? X power x into 1 plus log x. 1 plus, of course, log x to the base phi greater than 0. And everybody knows that this is strictly positive always. X bar x is positive because its domain is nothing but positive real numbers or non-negative real, positive real numbers. Therefore, it is positive. So for this big expression to be positive, what should happen? 1 plus log e must be greater than 0. Its derivative is x power x into 1 plus log x. 1 plus log x is greater than 0. This is always positive. So in order to observe that the function is increasing, this must be positive. That is, what should happen? 1 plus log x must be greater than 0, or log x must be greater than minus 1. That is, x must be greater than e power minus 1. That is, x is greater than 1 by e. What is the right option to be pointed here? This is open interval 1 by e2, 1 by e to infinity. Like that we proceed. Like that we proceed. So simply by observing the nature of the first derivative, that is f dash x, we decide whether it is positive or negative or non-monotonic. If you are not able to decide in a particular interval, sometimes it is positive, sometimes it is negative. If such thing happens, we do not say that the function is not monotonic in that interval. Well, one more important concept that must be studied in applications of derivative is concavity and convexity. Actually speaking, these two words are generally, so many people think that these two words are related to physics. In the chapter light or lenses or some other thing, we observe these two words, concavity and convexity. Keeping the shape of those concave and convex lenses in physics, if at all it occurs for us to look at a function, that is a graph of a function in that absolute picture, we name that the function is concave or convex. How can you decide? Look here. Observe the graph of the function. Observe the graph of the function. In this region, in this particular region, the graph is observed like this, opened downwards. In this particular region, the graph is appearing just like concave upwards, isn't it? It is opened upwards. Opened upwards. With this, we say that the curve is convex in this interval and concave in this interval. Okay, is it the only way to decide the nature of the function simply by looking at the graph, or is there any mathematical way to decide the nature? That is the special corner on which we may have to focus our entire attention. Yes, we focus our attention on that particular concept. Well, when can you say that a particular function is convex or concave? If you want to say that the particular function is convex in a particular region, say in this region the function is convex. Function is convex. What should happen? It is f dash x must be less than 0. And in this region, in this interval, say in this particular interval, the function is concave. How can you decide? You must be able to observe that f double dash x must be greater than 0 in that region. In that region. Yes. F double dash x is less than 0 for this shape, and f double dash x is greater than 0 for the shape. There might be some more functions, some other functions for which f double dash x equal to 0. Of course, that is the special case, and the point at which f double dash x equal to 0 is called a point of inflection. A point of inflection. Very rarely we come across those points of inflection, and here at this juncture, to look at that heading concavity and convexity, we may have to observe either f double dash x less than 0 like this, or f double dash x greater than 0 like that. If f double dash x, that is the second derivative of f of x, is positive in a particular interval, then we say that the function is concave in that region. Is concave in that region, and f double dash x less than 0 implies the function is convex in that region. We shall now look at some examples of concavity and convexity and some special character of concave and convex functions now. Let us consider the function f of x is equal to sin x. We know that it is everywhere continuous and differentiable at every real number also. Well, let us observe that what is f dash x? Cos x. What is f double dash x? Minus sin x. Minus sin x. Well, when x belongs to 0 to pi, observe the sine function. Observe the graph of the sine function 0 to pi. Between 0 and pi, the graph of sin x lies above x-axis. So sin x is positive. So minus sin x is negative. So f double dash x is negative. Therefore, the function, that is f of x equal to sin x, is convex in the region 0 to pi. Convex in the region 0 to pi. Whereas you observe the graph of the same function between pi and 2 pi. What happens? Between pi and 2 pi, graph of sin x lies below x-axis. Lies below x-axis. That is, sin x is negative. Therefore, minus sin x is positive. That is, f double dash x is positive. As f double dash x is positive, we say that the function is concave in that region. So f of x equal to sin x is convex in the closed interval 0 to pi, and it is concave in the interval pi to 2 pi. Well, let us see one more example, that is f of x equal to cos x. F of x is equal to cos x. What is f dash x? What is f double dash x? Minus cos x. Look here. Of course, without looking towards f double dash x, we can be in a position to say the nature of f of x equal to cos x about concavity and convexity. You please look at the graph. Between minus pi by 2 and pi by 2, the graph of cos x lies above x-axis. It is positive. So cos x is positive. So minus cos x is negative. Therefore, f double dash x is negative. Therefore, f of x is equal to cos x must be convex in the interval minus pi by 2 to pi by 2, and it will be easy to look at. We can confirm that by justly looking at the graph. It is concave, it is convex in the interval minus pi by 2 to pi by 2. Similarly, between pi by 2 and 3 pi by 2, what happens? Between pi by 2 and 3 pi by 2, what happens? The graph of f of x equal to cos x lies below x-axis. That is, it is negative. Cos x is negative. So minus cos x is positive. Minus cos x is positive. Therefore, what is say about it? Minus cos x is positive. Therefore, f double dash x is positive. So in that interval, in that particular interval, the function is concave. The function is concave. Yes. Moreover, there are so many applications of this concavity and convexity in numerical problems we will come across while solving them. F of a plus f of b by 2 is less than or equal to f of a plus b by 2 for convex thing. F of a plus f of b by 2 is greater than or equal to f of a plus b by 2 for concave functions. Like that, we will be able to observe and use in numerical problems. This is the crucial and the conceptual part involved in concavity and convexity of functions. For both of them, to make the decision for both of them, we must be able to have f double dash x. And if f double dash x is equal to 0, then it is neither concave nor convex. And that point at which f double dash x equal to 0 is of course called a point of inflection. Okay, what are the next after noting concavity and convexity, what happens when f dash x is equal to 0? If f dash x is greater than 0, the function is increasing. If f dash x is less than 0, the function is decreasing. If f dash x is equal to 0, it is neither increasing nor decreasing. Then what do you call about that? Stationary. So those points of x for which f dash x is equal to 0 are called stationary points. The importance and the important role of stationary points in locating the maximum value, minimum value, local maximum, local minimum, etc. All these things will be dealt under the heading maxima and minima later. After discussing the main concepts regarding some more applications of derivatives, namely tangents and normals. Yes, we switch over to deal with the concept of tangents and normals in the applications of derivative. First of all, what do you mean by a tangent? If a particular curve is given, the line which meets the curve at exactly one point is just nothing but called a tangent, which cuts the curve exactly at one point is nothing but called a tangent. For example, observe this. Let this be a curve given. The line does not meet the curve at all. This line cuts the curve at 2 points, of course. And now you observe this line. That line, which is expressed with dots, meets the curve at exactly 1 point. This is called the tangent to the curve at that point. We shall now take interest in finding the equations of the tangent, length of the tangent, properties, methods of finding, and its history using derivatives. How can it be done? This is now our job. Let us now concentrate on tangents and normals using derivatives. Let us observe the graph. Let this be the curve y is equal to f of x. Consider the chord AB where A and B are 2 points on the graph. Let this be the point. Let A is equal to A comma f of A, B is equal to A plus H comma f of A plus H. This is A. This is A plus H. This height is f of A. This height is f of A plus H. This height is f of A plus H. Okay. A is the point A comma f of A, and B is A plus H comma f of A plus H. Okay, the 2 points are now imagined like that. You please tell me the slope of AB. Slope of AB. From the knowledge of coordinate geometry, if this is considered as x1, y1 and that is taken as x2, y2, what is the slope of AB? y2 minus y1 by x2 minus x1. According to that, come on, tell me, what is the slope? F of A plus H minus f of A by A plus H minus A is nothing but H. Is nothing but H. Okay, now you take limits on both the sides as H tends to 0. Limit as H tends to 0. What happens? No proof is required for this. Slope of AB is f of A plus H minus f of A by H. Everybody can say okay. We have just taken limits on both the sides as H tends to 0. Now you try to understand what happens to the fate of AB as H tends to 0. What is H? The difference between, the distance between these two. If H is lessened, the point falls down. Still decreased, points falls down. Still decreased, if H tends to 0, then what happens? B tends to A, isn't it? Isn't it? Therefore, H tends to 0 implies B tends to A. AB tends to tangent at A, isn't it? If H tends to 0, then B tends to A. Then what is the shape of AB then? It becomes the tangent at A. Therefore, limit as H tends to 0, slope of AB is nothing but slope of the tangent at A. Okay. What is the fate of RHS? Limit as H tends to 0, f of A plus H minus f of A by H. It is just nothing but, come on, it is just nothing but f dashed A. F dashed A. This simple discussion tells us the way to have slope of the tangent at a point x is equal to A on the curve is equal to f of x. What is that? F dash A. What is the slope of the point, slope of the tangent at x1, y1? F dash x1. What is the slope of the tangent at a point B? F dash B. What is the slope of the tangent at a point x is equal to C? F dash C. Point x is equal to C means what is the y coordinate of the point? F of C. There is a point C, f of C. What is the slope of the tangent? F dash C. There is a point alpha, x is equal to alpha on the curve. What do you mean by that? The point is alpha comma f of alpha. Y coordinate is f of alpha. What is the slope of the tangent at the point x equal to alpha? F dash alpha. Justly because of this simple discussion, we will be able to declare, dictate and decide that f dash x becomes the slope of the tangent at x. F dash x1 becomes the slope of the tangent to the curve at the point x equal to x1. Like that. Okay. Therefore, in our formal way, if you write y is equal to f of x, y is equal to f of x, actually what is f dash x? dy by dx. What is f dash dA? What do you mean by f dash dA? dy by dx at x is equal to a. At x is equal to a and y will be accordingly f of a, of course. And this symbolism we use hereafter to know the slope of a tangent, slope of the tangent at a point on the curve, at a given point on the curve, y is equal to f of x. So, this is a valuable discussion which has given us the idea of evaluating the slope of the tangent at a point on the curve y is equal to f of x. Yes, we shall now use this concept further. And we believe that this is the right occasion, of course, to bring the word normal onto the stage, onto the fray. Yes, what is a normal? How to find its equation? Of course, that is the of a special interest is the case for us to deal with that heading, the equations of tangent and normal. How can we get it? Look here. Let this be the curve y is equal to f of x. Let this be the point x1, y1. Automatically, this is the tangent at the point x1, y1 on the curve. You please notice, you please study the graph carefully. This is the graph of a function, say y is equal to f of x. Graph of a curve rather, y is equal to f of x, on which a point x1, y1 has been given. We are now to have the equations of the tangent and normal. Look here, this is tangent. What is meant by normal? It's just nothing but observe the line. It is basically perpendicular to the tangent at the point and through the point. It's nothing but the normal. What is the normal? The line through x1, y1 and perpendicular to the tangent at x1, y1 is just nothing but the normal. Well, in the previous discussion itself, we have noted that f dash x1 is equal to dy by dx at x1, y1 is nothing but slope of the tangent at x1, y1. Let me call this m. According to our usual habit to represent the slope of any line, let me call this m. What is m? Slope of the tangent at x1, y1. What are the general methods or general system, general customary habits to represent slope of the tangent? One way is f dash x1. Another way is dy by dx at x1, y1. Another way is m. Well, we have known the slope and the point is also given. So what is the equation of the tangent? Y minus y1 is equal to m into, with the basic knowledge of straight lines from coordinate geometry, we have known the slope of the line and have the point x1, y1 also. Therefore, equation of the tangent is y minus y1 is equal to m into x minus x1. This is, of course, equation of the tangent. What can you say about the normal? It's very simple. Just slope changes. isn't it? You please recall that a normal is just nothing but a line perpendicular to the tangent. If the slope of the tangent is m, automatically slope of the normal will be minus 1 by m, because these two are perpendicular. Hence, can you guess the equation of the normal? It's very simple. What is that? Y minus y1 is equal to minus 1 by m into x minus x1. Y minus y1 is equal to minus 1 by m into x minus x1. What is m? As explained previously, what is m? It is just nothing but dy by dx of x1 y1. Do you believe that it is the slope of the tangent? Yes, of course. The previous discussion helps us to agree with the proposal that it is nothing but the slope of the tangent at x1 y1. Therefore, this is the equation of the tangent and that is the equation of the normal. Okay. So, equation of the tangent is y minus y1 is equal to m into x minus x1, and equation of the normal at x1 y1 is y minus y1 is equal to minus 1 by m into x minus x1, where m is dy by dx at x1 y1. Well, two more concepts are also there, namely subtangent and subnormal. What are they? What is the importance for that? We shall now look at. Observe the diagram very carefully. This is the graph of a curve, that is y is equal to f of x. Y is equal to f of x. It has been given that x1 y1 is a point on that. X1 y1 is a point on that. As this is the point x1 y1, the foot of the perpendicular of P on x-axis is of course x1 comma 0. Now you observe, this is PT is the tangent at P, Pn is the normal at P. Here what T is? The point where the tangent meets x-axis. What is N? The point where the normal at P meets x-axis. Good. PT is called length of the tangent. Pn, length of the normal. You listen to these words very carefully. What is the length of the projection of PT on x-axis? Tm. What is it? What is it? What is it? Length of the projection of the tangent on x-axis. Tm. Nothing but called length of the subtangent. We take much interest in finding its length only. Do you want to have the equation? It's just nothing but x-axis, isn't it? It is a part of kith and kin of part and parcel of x-axis, isn't it? So, nobody takes interest in imagining the equation. We take interest just in finding the length. What is this length? This is the length of the projection of this tangent on x-axis, called length of the subtangent of the curve at the point x1 y1. Absolutely in a similar fashion, you observe Mn. The length Mn is nothing but the length of the projection of the normal on x-axis. That is termed as length of the subnormal. Length of the subnormal. Okay, what is PT? Length of the tangent. What is Pn? Length of the normal. What is Tm? Length of the subtangent. What is Mn? Length of the subnormal. Okay. Let me abbreviate this as LT, length of the tangent. Ln, length of the normal. This length, length of the subtangent. This length, length of the subnormal. Length of the subnormal. So, That is the theoretical meaning of the words length of the tangent, length of the normal, length of the subtangent and the length of the subnormal. They can easily, very easily be understood by simply looking at the diagram, or rather the graph of the given function, in which subtangent, subnormal, tangent and normal are demonstrated. Yes, of course. Now, is there any formula to find those lengths? We create or we derive. It's not impossible. Equation of the tangent is y minus y1 is equal to m into x minus x1. What is it? What is it? The tangent. Well, I want to know the point T. How can you get that? It's very simple. It is just nothing but the point where the tangent meets x-axis. On x-axis, y is equal to 0. If you put y is equal to 0, x minus x1 is equal to minus y1 by m, isn't it? Or x is equal to x1 minus y1 by m. x1 minus y1 by m. Okay. Therefore, the point T is, come on, what is this point? x1 minus y1 by m, comma 0. Comma 0. Exactly in this way, can we obtain n? Why not? Why not? Look here. What is the equation of the normal? Y minus y1 is equal to minus 1 by m into x minus x1. What is the equation of the normal? Y minus y1 is equal to minus 1 by m into x minus x1. From that, our motto is to find n. Our purpose is to know n. How can you get it? You just take y is equal to 0. That's what I mean is you try to find the point where the normal meets x-axis. And on x-axis, y is equal to 0, isn't it? You take y is equal to 0. What happens? X minus x1 is equal to my1, or x is equal to x1 plus my1. Now we are ready to give the formulae for length of the tangent, length of the normal, length of the subtangent and length of the subnormal also, simply by looking at the graph itself. We can. Let us see. Just for the sake of calculation purposes, just removed x-axis and y-axis to save some space, that's all. Now, my purpose is to know length of the tangent is equal to distance between these points. x1 minus of this is y1 by m whole square, that is y1 square by m square plus y1 square. So that if you can simplify this, that is y1 by m into root of 1 plus m square. y1 by m into root of 1 plus m square. As this is length only, we are supposed to put modulus symbol. Success! This is the length of the tangent. Well, length of the normal. What is length of the normal? This is x1 y1. This is x1 plus my1, 0. Distance is x1 minus of this is m square y1 square plus y1 square. If you bring y1 out, good. So it is y1 into root of 1 plus m square. About length of the subtangent, is it not the distance between these two? This is x1 0, this is x1 minus y1 by m comma 0. Difference between x coordinates is modulus of y1 by m. Okay, what is the length of the subnormal? Is it not the distance between these two? Yes, of course. It can be read out. It can be read directly. No question of any calculation. Come on. There is x1 plus my1. That this is x1. What is the difference? Just my1. Therefore, length of the subnormal is equal to my1. Why should you put modulus symbol? Because they are just absolutely the lengths only. That is why we have taken the absolute value symbol, that is modulus symbol. Okay, let us gather all those things at a glance. This is length of the tangent, modulus of y1 by m into root of 1 plus m square. Then what is the length of the normal? This is nothing but modulus of y1 into root of 1 plus m square. There it is available. Next, length of the subtangent, modulus of y1 by m. Length of the subnormal, modulus of y1 into m. So, this is a very useful bunch of formulae. Length of the tangent, length of the normal, length of the subtangent, and length of the subnormal. Of course, here x1 and y1 are the coordinates of the point at which all this discussion is going on. M, what is M? Slope of the tangent at x1, y1. What is that? dy by dx at x1, y1. With the usual symbolism, we use that M like that. Well, length of the normal, length of the subtangent, and length of the subnormal. Here, so many important, beautiful things can be derived. What is the product of length of the subtangent and length of the subnormal? What happens? You see, it is nothing but y1 square. That is ordinate whole square. Ordinate whole square. Okay. What is the quotient of length of the tangent and length of the normal? What is the quotient? What is length of the tangent by length, or length of the normal by length of the tangent? What is that? It is m. Likewise, you can derive, you can use, you can create as many results as you want and as you can by making use of these 4 results. This is about length of the tangent, length of the normal, length of the subtangent, and length of the subnormal. Yes, it is important to note them down in your mind, to reuse them as and when they are required. Yes, we shall now switch over to a new topic, namely angle of intersection of two curves. Angle of intersection of two curves. Suppose observe the diagram. There has been given 2 functions, rather 2 curves. One is y is equal to f of x and y is equal to g of x. These are meeting at a point x1, y1. That is, x1, y1 is one of the points of intersection of the 2 curves. What do you mean by that? 2 curves may intersect at more than one point. We just do not bother about that. Let us consider one such point of intersection. What is x1, y1? One of the points of intersection of the 2 intersecting curves, y is equal to f of x and y is equal to g of x. You see, the word angle from geometry is meant very precisely, very accurately. Now it is our duty, rather it is our responsibility to define the angle between these 2 curves. The angle between these two curves is just nothing. It is defined as the angle between the tangents at one of the points of intersection. At one of the points of intersection. Y is equal to f of x. Y is equal to g of x. They meet at the point say x1, y1. They meet at the point say x1, y1. A tangent to this curve and tangent to that curve, two tangents can easily be drawn. One tangent to this curve and one tangent to that curve at the point of intersection. Well, let the slope of this tangent be m1, let the slope of this tangent be m2. Then the angle between their tangents is just defined as the angle between the curves. Of course, tan theta is equal to m1 minus m2 by 1 plus m1 m2, and to be more precise, in most of the cases we like to consider the acute angle of intersection between two curves only. In such a case, the acute angle between the two curves is given by tan theta is equal to modulus of m1 minus m2 by 1 plus m1 m2, isn't it? From the knowledge of coordinate geometry. From the knowledge of coordinate geometry, we recall that the angle between those two tangents which have been drawn at one of the points of intersection, that is x1, y1, is nothing but tan theta is equal to m1 minus m2 by 1 plus m1 m2. And as we have just discussed, as we take interest in finding the acute angle of intersection between two curves only, then tan theta is equal to modulus of m1 minus m2 by 1 plus m1 m2. We generally take interest in having the acute angle between the two curves. So that it is tan theta is equal to modulus of m1 minus m2 by 1 plus m1 m2. Of course, m1 and m2 can easily be obtained. What is m1? Slope of the tangent at the point x1, y1 on y is equal to f of x. That is just nothing but d by df dash x1. Automatically g dash x1 becomes m2. And tan theta is equal to m1 minus m2 by 1 plus m1 m2. Well, what happens when these two tangents are perpendicular? That is, when the angle between the tangents is 90, what do you say? That the tangents are perpendicular. But we say that the curves are orthogonal, not perpendicular. What is the special meaning of orthogonality? Nothing but perpendicularity. Well, I like to quote a beautiful example here. We sharpen the pencil with a blade. We cut a tree with an axe. Both are examples of destruction. We do not cut a pencil with a blade. We do not sharpen a tree with an axe. That is cutting, this is sharpening. Even though both the works are pieces of destruction, we use different words because the context is different. Absolutely in the similar manner, even though the angle is 90, as they are lines, we say that they are perpendicular. As these two are curves, we say that they are orthogonal. They are orthogonal. As and when you speak of the angle between the tangents of two curves at a point of intersection to be 90, then we say that the curves are orthogonal. In the case of circles, parabolas, ellipse, hyperbola, in all these curves, if at all you observe that the angle of intersection is 90, then the curves are said to be orthogonal but not perpendicular. Just a matter of a new word, that is orthogonality. Orthogonality. So, in order to observe the orthogonality of two curves, what should you have? the product of the slopes of the two tangents that drawn at x1, y1, which is of course one of the points of intersection, must be -1. That is m1 into m2 is -1, isn't it? That is, the angle between the tangents is 90. Then we say that the curves are orthogonal. Well, let us observe, rather witness some very simple examples about the angle of intersection of curves. In this session, we shall go through some more important problems and main concepts regarding angle of intersection of curves. Look at the problem given on the board. There are two curves. He has asked us the angle of intersection of these two curves. Actually speaking, frankly speaking, first of all, you must be provided with a point of intersection, but he has not provided, so you may have to find it. You see, solving those two equations is not so easy, but of course it's not difficult. It is not so easy. So for the present, let us assume that a point of intersection of those two curves be some x1, y1. Okay. First of all, let me have the slopes of the tangents at x1, y1. Differentiate it with respect to x on both sides. What is going to happen? 3x square minus 3 into u derivative into v plus v derivative into u is equal to 0. So that 3x square minus 3y square minus 6xy dy by dx is equal to 0. From this, dy by dx is equal to 3x square minus 3y square by 6xy. That is, slope of the tangent at x1, y1 on the first curve, let me represent it with the symbol m1, is equal to x1 square minus y1 square by 2x1, y1. 2x1, y1. Okay. What is x1, y1? I am supposing that x1, y1 is one of the points of intersection of the two curves. Okay. Differentiate this with respect to x. 3 into 2x into y plus dy by dx into x square minus 3y square dy by dx is equal to 0. Is equal to 0. So that you can cancel 3 on both sides. So that dy by dx into x square minus y square is equal to minus 2xy. Automatically, m2, which I am representing as the slope of the tangent x1, y1 on the second curve, that is m2, is equal to minus 2x1, y1 by x1 square minus y1 square. And it is an easy matter, very easy matter to look at that m1, m2 is simply minus 1. x1 square minus y1 square by 2x1, y1 and minus 2x1, y1 by x1 square minus y1 square. Clearly, m1, m2 is equal to minus 1. Product of the slopes of the two tangents at one of the points of intersection, that is x1, y1, is minus 1. Therefore, the two tangents are at right angles. So, the angle of intersection of the two curves is 90, or simply they are orthogonal. Here, one facility is involved in the problem. What is that facility? It is needless to find the point of intersection. You can observe. First of all, why do you hesitate to find the point of intersection in the beginning itself? It's not a very easy process. Of course, it might not be difficult. That is why, for such problems, we shall simply take in our mind that one of the points of intersection is x1, y1 and proceed. Luckily, by proceeding in this way, we could have observed that m1, m2 is equal to minus 1. Therefore, the angle of intersection of these two curves is simply 90, or they are at right angles, that is, they are orthogonal. Well, now let us observe one more such famous problem. In the next question, which is of course very famous, he has given us two types of an ellipse. This is an ellipse, this is an ellipse, and he is saying that those two ellipses are orthogonal. What is the condition required? That is the question. Of course, it's very simple. Again, here also, let me assume that one of the points of intersection is x1, y1. Okay. First of all, subtract this. What happens? X square into therefore, the point of intersection of these two curves should satisfy this equation. That is, x square into plus y square into let us keep this at a side. We know that x1 square into a1 square minus a square by a square a1 square plus y1 square into b1 square minus b square by b square b1 square is equal to 0. We shall use this condition later. First of all, these two must be orthogonal according to the question. According to the question, these two curves are orthogonal. What is the condition required? That is the actual question. Well, let us recall the condition of orthogonality. When do you say the two curves are orthogonal? The angle of intersection must be 90. If m1 is the slope of the tangent to this curve at x1 by 1, m2 is the slope of the tangent at x1 by 1 on this curve, then m1, m2 must be minus 1. Okay, let us make use of that. First of all, from this equation, what can you say? 2x by a square plus 2y y dash by b square is equal to 0. Isn't it? Okay, 2 will automatically be cancelled. What is y1? y1 is equal to minus x by a square, it is y dash. What is y dash? Minus x by a square into b square by y. b square by y. Therefore, this is m1. What I mean to say is slope of the tangent at x1, y1 on the first curve is minus b square x by a square y. b square x1 by a square y1. Why? Because I am assuming that one of the points of intersection of the two curves is x1, y1. I am taking m1 is equal to like that. In a similar fashion, you can assume that m2 is equal to minus b1 square x1 by a1 square y1, because there are no more changes except a1 and b1. But it has been given that the two curves are orthogonal, so what should I have? m1 m2 is equal to minus 1. But m1 m2 is equal to minus 1. This product must be minus 1, that is b square b1 square by a square a1 square into x1 square by y1 square must be minus 1. Must be minus 1. Now, this is the time for us now to utilize this condition. Let me call this 1. You see, what is x1 y1? Point of intersection of the two curves. It should satisfy this equation. So, x1 square into this much plus y1 square into this much is equal to 0. From this, what is x1 square y1 square? What is x1 square by y1 square? What can it be? divide it throughout with y1 square. What is going to happen? This is x1 square by y1 square is equal to minus b1 square minus b square by b square b1 square into a square a1 square by a1 square minus a square, isn't it? Good. From this, you can have b square b1 square x1 square by a square a1 square y1 square is equal to minus of b1 square minus b square into etc. Isn't it? Implies b square b1 square into x1 square by a square a1 square into y1 square is equal to minus of b1 square minus b square by a1 square minus a1 square, minus of b1 square minus b square by a1 square minus a square is equal to minus 1. You can cancel minus 1 on both sides. All together you have a square minus a1 square is equal to b square minus b1 square. That must be the condition required, which is of course very famous. One of the most standard results of orthogonality. So what is the condition required? A square minus a1 square is equal to b square minus b1 square, or a1 square minus a square is equal to b1 square minus b square, which is the required condition of orthogonality of the two curves given. A beautiful question.